Hi, everyone. There's I put this announcement on D2L regarding these study sessions. They're Wednesdays from 1 to 2 and Fridays from 11 to 12. So those are provided for this course. If you're interested, it says stop by the Academic Success Center in the library, L245, to find out more information. So if those work with your times, feel free to stop by the library and attend. Yeah.
There's another one from 12 to 2.
On what day?
Friday.
On Friday from 12 to 2.
Yep, with Renee something.
Meston or Swindle? Meston?
Yeah.
Okay. Yeah, I'll wait for them to send me. I don't know if that's like a one-on-one thing or.
It's anybody that wants to show up with her.
Okay, so maybe tentatively from 12 to 2 on Fridays as well. I haven't received confirmation for that one, but if you're interested, there's the information. Additional study groups always beneficial. Does anyone have any homework questions? So we've done 3.1, 3.2, 3.3. We started 3.4. 3.4 was the product rule. And what do we? So we've shown here that to take the derivative of a product, you can't just take the two functions derivative and then multiply them together. So the product rule says that we have to take the first factor times the derivative of the second plus the second factor times the derivative of the first. And I think that's about as far as we've got. So the product rule, again, just another derivative rule that you've got to keep track of, you've got to know. And for instance, finding the derivative of x times e to the x. A lot of times what we look for is like, can we simplify that? Can we make the function simpler before we take the derivative? In a lot of instances you can't. So x e to the x can't really do anything with that. So it's the label of first and second it's totally arbitrary. You just have to have one product or one thing times another thing. It doesn't matter what you call first and second. What matters is that you're stating the derivative rule correctly. So we could call e to the x the first and x the second factor or what have you. So just for simplicity, that's the first, this is the second. And so f prime then is taken by the first times the derivative of the second. So we've got x first times the derivative of the second. And I'm just going to explicitly write out the derivative rule as it is. I'm not going to try to take, when I say derivative in my head, I'm not going to try to take the derivative right there on the spot. I would recommend you do the same thing because when we get into 3.7 and start looking at the chain rule, it's going to be hard to take certain derivatives in your head, and it's going to be a lot more beneficial to take additional derivatives off to the side and work them. So we have the first times the derivative of the second plus the second times the derivative of the first. So we've set our product rule. Whatever other derivatives show up, then we'll compute those as necessary. And I know, these two derivatives are rather simple. We could have potentially done them in our head, but this is how we're going to write out our product rule, our quotient rule, and our chain rule when we get to 3.7. Okay, so derivative of e to the x is what? E to the x plus e to the x times the derivative of x, which is 1. So that's our derivative. So your derivative wouldn't consist of other derivatives. If you still have derivatives hanging out, like in our first step, you know that's not completed. Okay. Does that make sense? You gotta remember the product rule amongst all the other rules we talk about here. Second example, we've got 4e to the x times the square root of x. Again, it doesn't matter what we call the first. We could even utilize the properties of derivatives that says, if I'm going to take the derivative of this, I got the product of two functions of x, e to the x and the square root of x. What happens to that constant? Well, what can we do with that constant of 4 that's out front? So can we take the derivative and then just multiply it by 4 after we're done?
No, it's the same constant.
It's the same constant, right? Remember, we had the derivative rule. If it says you're taking the derivative of a constant times a function, that's the same thing as the constant times the derivative of the function. Y'all remember that? So if you wanted to, you can take the 4 out and multiply it in after you've applied the product rule to the e to the x and root x. If you want to consider 4 as a part of the first factor, then you can do that as well. It totally doesn't matter. So let's just call 4e to the x the first. And take the derivative. We have the first times the derivative of the second. And the square root of x, I'm going to write it as x to the 1/2. So when I take the derivative, I can apply the power rule. So there's the first times the derivative of the second, and then what's next? Plus
second times the derivative of the first.
the second times the derivative of the first. So that's the product rule. Now we need to find the derivative of each one here. We've got 4 e to the x. What's the derivative of x to the 1/2?
Wouldn't that be?
Yeah, 1/2 x to the negative 1/2. To do this here. Power rule 1/2 x to the negative 1/2. Okay. What's the derivative of 4e to the x?
Itself.
Itself, right? It's 4e to the x.
Could you also say for the derivative of the one up front, could you just say that as x over 2 raised to the negative 1/2 instead of 1/2 x? Or does it matter?
Say that again, x to the
Negative 1/2,
negative 1/2.
and then have the x over 2,
Uh-huh.
like that, but then have the exponent raised to, for the whole thing.
Like this?
Yeah.
Like for the derivative of this?
Yeah.
Yeah, that's the same thing.
Is it? Okay.
Or that's the same thing as this as well.
Okay.
Okay. Any other questions on that? That's our derivative.
And that's as, like on the exam, for example, that's as simple as you would want it. You don't want the.
Yeah, so on a lot of these more involved derivatives like this one, I'm just looking for, do you know how to take the derivative? I'm not going to ask you to simplify. There will be some on the exam where it says find the derivative and simplify if possible. But something like that, it would just be find the derivative, and then so you would just stop here. You know, I wouldn't worry about factoring out an x to the negative 1/2 of 4e to the x. If you didn't have to simplify it, that's it, you stop there. But it is noteworthy that we can simplify, like, especially in chapter 4, we're going to need to figure out where that thing has a horizontal tangent. So we're going to have to take derivatives like that, set them equal to 0, and then solve for x in chapter 4. a lot more than we have to do in Chapter 3. But on Chapter 3's exam, Chapter 3 is all about derivatives, so that's primarily all I'm looking for is, can you take the derivative correctly? And then as we move into Chapter 4, we'll sort of fine-tune what we're doing with the derivatives. Okay. Does anyone have any other questions on this one? So I promise the sooner you can start memorizing these derivative formulas, the better off you're going to be. Okay. So that's the product rule. The quotient rule tells us how to take the derivative of a quotient. And again, we see it's not as straightforward. We can't just take the derivative of the top divided by the derivative of the bottom. Okay. So a lot of times, I mean, there's a couple of ways people remember this by calling the top function the top and the bottom function the bottom, or the top function, the numerator, that sometimes is referred to as high, and the bottom function is low. So there's, you know, high D low minus low D high. We'll write both of them down, just so you can kind of pick which one you want to choose to remember. Over here, so the derivative of the top over the bottom. Either way, it's our quotient rule. You have to take the bottom times the derivative of the top. Minus the top times the derivative of the bottom. And then we have to divide all of that by the bottom squared. Now, typically when we write out the derivative of a quotient, you don't square out that bottom function. It's just left as the bottom function squared. So we don't usually worry about expanding that. Or the high over the low. Derivative of that low, D high, minus high D low. Over low squared. Sorry, I'm not being consistent with my capitals and lowercase. But either way, that's how we take the derivative of a quotient. So start remembering whichever one makes most sense to you. It's also worth pointing out that when you take the derivative of a product, that in practice it's going to matter the order, but when we look at the first times the derivative of the second plus the second times the derivative of the first, it doesn't matter what order we have that in, right? We could say it's the derivative of the second times the first plus the derivative of the first times the second. You know, it doesn't matter how we order that since they're multiplied and added together. With the quotient rule, though, it's very specific as to which one gets subtracted on the top. So you've got to subtract off the top times the derivative of the bottom. So just be super mindful of that order because it matters. So, use the quotient rule to find the derivative of x plus 1 over x plus 2. So I don't know, did everyone get a chance to copy down what they needed? Okay. So we're going to take the bottom quotient rule, bottom function times the derivative of the top. And again, I'm just going to write all of this out as I'm saying it. Bottom times the derivative of the top minus the top times the derivative of the bottom. And then I'm going to divide all of that by the bottom squared. It's also important to realize that when we're subtracting off the top times the derivative of the bottom, that all of that is that whatever that product is, all of it's being subtracted. If you want to put like a -1 out front in brackets, just to remind yourself what's happening, you know, it's really plus a -1 times all of this stuff. That's another way to think of it. I think one of the main issues with quotient rule stuff is the distribution of that negative to your second half on the top, I guess. So there, we've said the quotient rule, and then we're going to address the individual derivatives that show up. So we have our x plus 2. What's the derivative of x plus 1?
1.
Does everybody agree? Derivative of that is 1. So I'm just going to write that there, times 1. We have minus x plus 1. Derivative of x plus 2, also 1. And then we have all over x plus 2 squared. So we're just going to leave that x plus 2 quantity squared like that. And so that's just x plus 2 minus the quantity x plus 1 all over x plus 2 squared. So again, I hope no one's in this habit, but it is absolutely incorrect to just divide these. Both of those things on top are divided by x plus 2 squared. So don't just simplify the x plus 2 because they're the same. We need to actually simplify the top or factor an x plus 2 out before we cancel it with the bottom. So we've got our x plus 2. This is just going to be rewritten as minus x minus 1. So we have 2 minus 1 on top, all over x plus 2 squared. And that's our derivative. And we simplified that because it wasn't that much effort to simplify, just combining like terms. Anybody have any questions on that? Okay, so we'll look at a couple more, but you know, when we look at things like taking the derivative of 1 over x to a power, let's say, like 1 over x cubed. Now we've got two ways to look at that. We can look at it either as a quotient, or we could say that's the same thing as taking the derivative of x to the -3rd power and use the power rule there. Most every single time it's going to be easier to do those things with the power rule. So if we do the quotient rule, we will see that it is the same, but we have to take the bottom function times the derivative of the top minus the top times the derivative of the bottom, and then divide all of that by the bottom squared. Is everybody okay with that? When you use the quotient rule, you never take the derivative of your entire quotient. Never does that show up anywhere. We always think about it as top over the bottom or high over low. What's the derivative of 1? Derivative of 1 is 0, so all of this stuff is 0. Derivative of x cubed, 3x squared. And then we have all of that over x to the power of 6. We'll just simplify what we have. We've got a negative 3x squared over x to the 6th, which simplifies to negative 3 over x to the 4th. So I don't know. Well, that's the derivative. We didn't actually label it f, but that's the derivative according to the quotient rule. And if we use the power rule on x to the negative 3rd, the derivative then is negative 3x to the, what power? Negative 4. Subtract 1 from the original power. And we see once we write with positive exponents, they're exactly the same. Any questions on either of those? Yeah. This negative 1 from the minus in the quotient rule. So we had minus the top times the derivative of the bottom. So that's where that negative 1 came from right there. But it's really part of that second term of the quotient rule. The formula just has that minus built in, and then we have top times the derivative of the bottom. So again, whatever we had here in these red brackets, if we had like 5 terms, that negative needs to be distributed to all 5 of those terms. Yeah.
Wait, isn't the derivative of the constant the constant, right?
Which one?
For like the derivative of 1, isn't that just 1?
Oh no. No, so because we're not taking here, right, with the green part it is, because we're actually taking the derivative of it. But that second term, it just says subtract off the top function multiplied by the derivative of the bottom. So we're only taking the derivative of the bottom when we have that piece on top, if that makes sense. So if we had the derivative operator here on the negative 1, then all of it would be 0. But we don't. It's top times the derivative of the bottom. Yeah.
So the x cubed times the derivative of 1 is 0.
Yes, in the green right here. Yeah, that turned into 0. We didn't actually write that out. We should write that out. So we had that x cubed times that derivative, which was 0. Yeah. Any other questions? So it is entirely possible now with products and quotients to see both in the same function. So x squared times e to the x divided by x squared plus 1. We find the derivative of that. So this is where things start to can have a tendency to get even more confusing than maybe they already are. I don't know. You've got to look at the structure of your function. So, maybe, I don't know, when I looked at that initially, my mind immediately went to product rule because I have a product on the top. But we're not going to apply the product rule to take the derivative of that function because that function is a quotient. Okay? So we're not worried about the product rule at this point. We're just going to say, all right, well, my function is a quotient, and I need to apply the quotient rule. It doesn't matter if I had like 4 products up top over 2 products on bottom. Like I'm not like even getting that far ahead. I'm just thinking, all right, well, that function is just a quotient. It's this thing divided by this thing. Everything else will take care of itself if I'm writing my derivative rule down correctly. Is everyone clear with that? So don't jump ahead. Okay, so quotient, we're going to apply the quotient rule to this here. We're going to say it's the bottom function times the derivative of the top minus the top times the derivative of the bottom. And then all of that's over the bottom squared. So I'm not even going to worry about the complexity of the function. I'm just going to identify what kind of function it is. That's going to tell me what kind of derivative rule to apply. And then other derivatives do show up. So that's fine. I'm just going to separate out those derivatives, maybe off to the side or down below, and compute those accordingly. So now when I compute the derivative of this thing, what am I going to use? Yeah, that's when I'm using the product rule. Okay, so we're going to find the derivative of this thing in red. Once we find these derivatives here, we're done with the derivative, right? But we have additional derivatives we've got to find. So let's go down here and find these additional derivatives. So the first one was the derivative of x squared e to the x. So we sort of separated that out, identified now that thing we got to take the derivative of is a product. So we're going to apply the product rule. We have the first times the derivative of the second plus the second times the derivative of the first. So most derivatives that we see do involve additional derivatives. But just like we're handling this one, those additional derivatives you're going to compute off to the side and just insert them back into the original derivative you took. That's how you know when you're done. Okay, so then we take the derivative of e to the x again. That's e to the x plus e to the x times the derivative of x squared is 2x. So we have that times our e to the x. So again, we know we're done with that because other derivatives aren't showing up. Which again is why I recommend when you say derivative of whatever function, explicitly write that out. That way you don't have to keep track of, oh, did I not take enough derivatives? Did I take too many derivatives? You know exactly what to take the derivative of. So this goes in place of this in red we have here. We have the x squared plus 1 times the derivative of x squared e to the x, which we found as x squared e to the x plus 2x e to the x. And then we have our other derivative showing up in our quotient rule, which was the function x squared plus 1. So maybe you can just do that immediately, but we're going to come down here. What's the derivative of x squared plus 1? 2x. Just 2x. So that's the derivative of that. We're going to put that in place of that derivative there. So we have our minus x squared e to the x times that derivative, which was just 2x. And it's still all over x squared plus 1 squared. So really, if you're not simplifying on the exam, like that's all I would really want. Does anyone have any questions? So why don't y'all take 5 minutes, compute the derivative of that, and then we'll work on simplifying it. Right now, just worry about the derivative and not simplifying the derivative.
This is making.
So that would just go there. That would be like derivative of x minus 7. For sure, if you're doing the same colors in the same way, that would be derivative of this. I know what you have, right? Yeah, you have that right, because that's a product. So you did that right. That's great. So that just needs to go in. What's it called? Derivative of x.
I've already messed up.
Because derivative of x. It would always be derivative of x.
Since this was covering as well.
Yeah, these goes for
Correct.
So this part is right. Just the product of this part. But does that mean you have to factor this and this one to simplify it, or could it just be this whole quotient is this?
Yeah, that's pretty much where we're at right now.
Oh, so just leave it at that?
Anything you do after this is going to be simplified. So that's what you can do.
Oh, this is both. I can just let this be answer.
Right.
Oh, okay. I was just like, I really don't want to simplify all this out. Like, that's just not what I want to do.
Did you simplify all the way? No. We're not. We're comparing.
You okay?
Yeah, I got to a point, I'm not sure how to simplify that.
What happened to this thing?
Nothing, this, this, I guess,
Okay, but this x plus 7 is distributed really multiplied here and here. So you would really have 2x squared with the x of those, and you have a positive 7 of those, right? So before you subtract this with this, you would have to expand all of that first. So that would actually, you would actually just.
It's the second part.
As the, like, that's the unsimplified version.
Yeah,
And then we'll just look at simplifying the second one.
which is just that, times the first one, or the second one.
Is it hard to do
Although, I did like 3.6 and 7 as well today.
a lot of reading? But I like reading.
This math looks really hard.
All you're doing is taking these, rewriting yeah, so it's just basically this minus this times this one, the derivative of this one, minus times the derivative of this one. Divided over that, square this one. So the big work is just final derivative. Two things being multiplied. you think about that? Okay, after you see the
I missed it Monday.
I can't imagine how this was science and
It's not until like
the same with chemistry. You said it's easy, but you can't.
And then you choose the answer.
So bottom times the derivative of the top. Minus the top times the derivative of the bottom. All over the bottom squared. And really, most of you had, the derivative version where you didn't simplify. Something like this on our exam, I wouldn't have you simplify fully, just because there's probably multiple ways people are going to simplify it, and it just makes it that much harder to grade, looking for like 5 different correct answers. So something like this, you would just find the derivative and then leave it alone. I wouldn't have you simplify something this complex. Okay, so product rule for that one, again, 2x squared e to the x. We have the first times the derivative of the second. So x plus the second times the derivative of the first. And then here, derivative, that derivative is of course 1. Okay, I need to move this down. Okay. That one's a 4x e to the x. So now I saw people doing various things. Everybody was doing what they should have been doing. It's just how you choose to organize could be as long as you understand what you're doing, I guess. But like organization is crucial when we're doing these kinds of things. Just so you're not like putting things where they don't belong. I'm not saying you have to write it out exactly how I write it out, but something close would probably be really beneficial. So the derivative is just our 2x squared e to the x times 1. So we're not going to write that. But we have minus the quantity x minus 7 times that derivative, which was 2x squared e to the x plus 4x e to the x. And then all of this was over the bottom thing squared. So really on the exam, that's all I would be looking for is is that you can just totally stop right there. It's kind of a pain to simplify because you've got to distribute the x plus 7 here and here, then the minus, and then combine like terms, factor out common factor, simplify the thing on the bottom. So I think the easiest way to simplify this is to take our red factor here and factor out the common factor of that, and then we can factor out that factor and this factor right here. Then you get some polynomial, you can simplify that. So like I said, in chapter 4, we do have to simplify these things. I don't know that we actually see anything that involved, but there are some pretty tricky ones that we end up seeing. So what I mean is that we're going to take the red portion and just the pieces and the terms in red, we're going to factor out our common factor. So let's write it like this. We're going to factor out a 2x e to the x. And that'll leave us with x plus 2. That. I'm going to go ahead and expand the denominator. 4x to the 4th. It's e to the 2x or e to the x times e to the x on bottom. And then we can factor out, because now up top we don't have, a thing multiplied by a sum in red, right? What we have up top now, once we factor that out, is we have these three things multiplying each other on top here. This thing times this thing times this thing. And then we also have this thing. So, like if we're just looking at it at a basic level, it's like A minus B times C times D is kind of what we have on top now. So we're just going to say, what does A and what do B, C, D have in common? And so what they have in common is the 2x e to the x. So what we're doing is looking at, all of this stuff here. Since those three are all multiplied together, we have common factor between A and B, C, D is what we're looking at. So we're just going to factor again a 2x e to the x out of both of those things in green. And so we have that here. Out of the first 2x squared e to the x, that's going to leave us with just an x. And we have our minus here. We didn't do anything with the x minus 7. We factored this out, so that's just 1 times that x plus 2. Okay, so that's the top, still over the bottom. So now we can simplify what we have in green and what we have on the bottom, right? Because it's multiplied. We're going to simplify what we can by dividing these two things. So 2 divided by 4, x divided by x to the 4th, and e to the x divided by e to the 2x. One of those. And then up top we simply have x minus this thing. And then so we just end up with this x minus this quadratic up top. So just write it here, x. We've got a x squared, and a minus 5x, and a minus 14. But all of it's times that negative out front. All over 2x cubed e to the x. So that's our simplified version.
Wouldn't that be 4x? Wouldn't that be 4x?
So
Where?
it's right?
Oh, no. Never mind.
It's a positive.
Yes. And, one of the main reasons we care about a simplified version is if we took that original derivative, the thing that we boxed up initially, and said we want to know where that derivative is equal to 0, you're still going to have to simplify it to figure out where it's 0 at some point. So typically the procedure is find the derivative, then simplify it, then set it equal to 0 and solve. One way or the other, you're going to have to do that. Okay, so you might have taken a different route where you can totally expand the second part of the numerator. Then you can collect your like terms with the 2x squared e to the x. Combine like terms there, then factor out the common factor, then simplify it with our denominator, 4x to the 4th. So, that's just one way to go about it. Any questions on any of that problem? Okay. Let's see, I think we have this. Yeah. Okay, so our last example here in 3.4. We've got a population of cells modeled by P of t is 400t over t plus 3, where t is larger than or equal to 0 measured in hours, and the population P is measured in millions. We want to compute the instantaneous population growth rate and identify the units. For part A, what are we asked to find? Yeah, the derivative, right? The instantaneous growth rate. Instantaneous rate of change is always the derivative. Here our rate of change is population growth, right? So we're finding P prime in part A. And we have a quotient, so we're going to apply the quotient rule, bottom, times the derivative of the top of t. 400t. Bottom derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. We have over here t plus 3. What's the derivative of 400t with respect to t?
400.
Just 400, yeah. And we have minus 400t times the derivative of t plus 3, which is 1. And then it's all over t plus 3 squared. Yeah. Up top we have 400t plus 1200 minus 400t. So we just end up with 1200 on top. T plus 3 squared on bottom. For p prime. So there's the instantaneous growth rate function for any time. If I wanted to know how fast that colony of cells was growing at 1.357 seconds, then I just plug 1.357 into that function. And I know at that precise moment, that's how many cells were being either produced, I guess, or eaten, taken away, whatever cells do to each other. What are the units, though, for p prime? So, like, if p prime came out to be 5, what does that mean? Or if p prime were 26, what does that mean? Which one? Millions of cells per hour, right? Anytime you take the derivative, you have independent, you have the y over the x for the units, right? dy dx. So we have the units for our dependent variable, p, divided by the units of our dependent variable, which is t. So our units are millions per hour. I don't know, whatever, however specific you want to get with that, but those are the units. So like if the derivative were 5, we would say that at whatever time that was, the population was growing by 5 million cells per hour. If it were -10, we would say that the population was decreasing by -10 million cells per hour. Okay, does anyone have questions on this? Yeah. Oh, right here? Right here? Okay. Any other questions? Okay, so another frequent question with these types of things, what is the steady state population? And I don't think we've ever talked about this. The idea of a steady state, whether it's, anything that you're measuring, a steady state just means, does it approach a specific number after a certain amount of time? So what that means is we're going to compute the limit as t approaches infinity. So maybe you're modeling like the spread of a disease, and you have a particular model, and it says, all right, well, this thing models the spread of that disease. And we want to know, is that disease eventually going to die out, or is it just going to keep growing? And so we would say, all right, well, with this model of this particular disease or epidemic or whatever, does it have a steady state? So we compute the limit at infinity. If the thing keeps going, the limit is infinite, and then we have a problem. If the limit at infinity dies off, then the number of people infected would also eventually reach 0. So that's, any kind of context. Steady state just means what happens over the course of time. So it's the limit as t approaches infinity. And it says, what is the steady state population? So you have to be super careful. Population is described as p of t, not p prime of t. Remember, p prime was the instantaneous population growth rate. So what's the steady state population? We need to compute the limit at infinity on p of t. And so once we compute this limit, we're going to be able to see exactly what's happening with that population. What was it, 400 t over, is that right? Yeah, 400 t over t plus t. Population function. Steady state population is What is it?
It'll continue.
Does it keep going forever? Could we compute a limit at infinity?
Leading terms.
Leading terms, it's a rational function, right? You've got a linear over a linear, so we just look at leading term over leading term. What's the limit at infinity? 400. What does that mean?
400 million people are gonna get. No, wait, is it cells?
Yeah, cells, right?
400 million cells.
400 million cells, right? Because the cells were measured a million, population was measured in millions, so this represents 400 million. That just means after, indefinitely, the population will reach 400 million, and it won't go higher than that. And then that's just whatever, it's environment, it's the container those things are in, whatever's happening, right? Like if you've got a number of fish in a pond, they're not gonna keep multiplying forever. They're gonna level out at a certain population. Bacteria in a jar, they're gonna level out at some certain population. They're not gonna keep growing forever.
Is there something that would actually go to the limit? Like to infinity?
Yeah, it could. It just depends on the particular model. Like if it were if our population function was, let's say, I don't know, 2 times e to the 0.4t over t plus 3, then that would go to infinity. So that population would grow forever. So yeah, there are cases. It just depends on what your model is. It certainly could happen. Okay, so 400 million implied to be that 400 million. So the steady state population is 400 million. If we looked at the graph of our population function, what would we have? A horizontal asymptote, right? As we progress indefinitely in that direction, the function approaches 400. So that's horizontal asymptote. Remember, limits at infinity determine this function's end behavior. So change our scale a little bit, but we have that being our horizontal asymptote. So we have stuff happening over here too, but this is all negative time. We don't concern ourselves with what happened in the past. So there's our horizontal asymptote, steady state behavior, steady state population in this case. I do want to look at also what happens if we compute the limit at infinity on the derivative, just to kind of compare these results. So like some of the questions in MML would say, what time's the instantaneous growth rate the greatest? Those are really hard to answer at this point. There's 2 ways to answer. How would we answer this question in part C? What time was the instantaneous growth rate the greatest?
0.
At 0? So how do you know?
Because at that point, that's when it's growing fastest on the graph.
On the graph of
4x over t plus 3.
the population, okay.
Right.
So remember, it says what time is the instantaneous growth rate? That's the derivative. So what time is the derivative the greatest? So when is the slope on the population graph the greatest, is what we're asking there, right? Does everybody agree with that? So that's one way we can answer that. So let me say at what time. Let me say at what time. The graph of is the slope greatest? Okay, so that's one way to answer it. Just put your pencil down on the curve, and then both of these, the way we're answering both of these is by using technology. So we're going to look at the graph of P of t. What else could we do?
Evaluate the derivative at 0.
Yeah, you could find the derivative. When is the derivative 0? Like, that's chapter 4 stuff. Certainly would work. We technically just haven't talked about that, so. But the other thing we could do along the same lines of graphing would be to do what? So we could say when the instantaneous growth rate is the greatest, we could just, since we have the instantaneous growth rate, could we just graph that and see where it's the highest? So we could also graph, and this takes a little less of the guessing out of it. So this is probably preferred to answer this question exactly. But we could graph P prime of t and find the highest point. Really, it's asking for what time, so we would just take the t value of the highest point. So here is our derivative. Is that right? Have to scale this a little bit more again. No, now it's unrecognizable. I'm looking for this thing up here. Well, that's now approaching an asymptote. Let's go back home. Let's show this. Okay, so we're just concerned with t equals to 0 and onward, so there's our graph. We can now locate a little bit easier the highest point here. So that's at t equals 0. That's when the growth rate, which is this function in green, that's when it's at maximum. Okay, so there's really two ways to answer that. And if we go back to our graph of the population function, we're just looking at that graph and saying, where's the slope the steepest? And so we're just still trying to eyeball it on that one, but either way. I'll stick this in our notes. Oops. Does anyone have any questions on that? So we really don't find max and mins by using calculus or algebra until chapter 4. Part D, if the limit as t approaches infinity on p prime of t equals to 0, what does this mean? So remember this limit right here, that's steady state. So we're computing the steady state of the growth rate function. Instantaneous growth rate. So if that derivative if the limit at infinity on our derivative is 0, what does that mean?
It stops growing.
It stops growing?
Yeah, it stops like growing or decreasing.
Do y'all agree with that? So what this is saying is the steady state of the instantaneous growth rate is approaching 0. So what does that mean about the growth rate? It's slowing down, right? If the rate of growth is eventually 0, you have no growth anymore. So that's kind of how we're interpreting that. It means the instantaneous growth rate approaches 0, which means if the growth rate is approaching 0 at some point, in time, the population will stop growing. And that does solidify what we did in an earlier part when we said what's the steady state population of that colony of cells or whatever. Like it ended up approaching 400 million, but it's approaching 400 million. It has to approach a specific value because it stops growing, and that's what this limit at infinity on the derivative tells us. The population eventually stops growing, therefore you should have a steady state population somewhere. If we needed to go back and find the steady state population, we would go back to part B and compute that.
For the last one, since it was 400, does that mean it'll be 400 going on to infinity forever, or like at a point decrease back?
So, like our work says that it's 400 forever. Like the population reaches 400 million, and it stays there forever. We know that's sort of impractical, right? But we would, since it's a horizontal asymptote, we would never expect it to like dip back down and start decreasing. In reality, it probably would. You win some, you lose some, right? So that's why there's, these models that predict things are just that. It's like, well, if you look at a weather forecast, like after 7 days, it's pretty bogus. Like it might be somewhat accurate, but they're also forecasting, they're predicting, they're saying, hey, based on current trends, this is what's going to happen. But a day later, all of that could change. It's just based on this model that I'm using currently, what would happen. And we could say that it would just stay at 400 million.
Do you think there would be like a way for us to actually be able to calculate like 100% what might happen in the future?
Yeah, based on what we have, like if we wanted something more accurate, we would just have to keep watching that thing and tweaking our model. And then what you get into is differential equations. Like how do things vary? How do things vary as their rates of change vary? So it starts to get a lot more complex than just calculus. But yeah, you could certainly get more accurate if we had a better model or paid closer attention to it. Yeah. Any other questions? All right, we'll take a break and then begin the 3.5 after break. All right, so in 3.5 we have the derivatives of our trigonometric function. Before we actually look at those formulas, we're going to look at these two limits. And these two limits are used to determine the derivative of sine and cosine. And once we have the derivatives for sine and cosine, then we can use their reciprocal relationships to find the derivative of secant, tangent, cosecant, and cotangent. So as far as the exam, there's no need to remember these two limits. I'm not going to test you directly over these limits. We're just going to go through some of these because they are in your homework. And both of these limits are involved in deriving the derivatives of sine and cosine, which is what we're going to talk about. So a few examples. One. The limit as x approaches 0 on the sine of 32x, sine of 32x over 32x. And so like, when you look at these limits here, the argument of sine is approaching 0, and the denominator is approaching 0. And the argument and the denominator, the argument of sine and the denominator are the same quantity. So that applies directly to the sine of 32x over 32. The argument of sine is the same as the denominator, both quantities approaching 0. That limit is equal to 1. So x doesn't just have to be x. But what's important there are those quantities are the same. So we could have, in general, this is true. The limit as x approaches 0, the sine of ax over ax is equal to 1, where a is a real number. Some of the other ones aren't as straightforward. You've got to like manipulate them a little bit. So, for instance, the limit as x approaches 0 on sine of 3x over x. So we've sort of like alluded to what that limit should be. But if we're trying to fit this in directly with that limit that we boxed above, again, this sine of 3x, the argument, and the thing on the denominator have to be the same before we apply that limit. So we can't just simply multiply the denominator by 3 without also multiplying the numerator by 3. So that's what we're going to do here. Multiply the denominator by 3 and the numerator by 3. So I'll just rewrite this here. It's the limit as x approaches 0, sine 3x over 3x, but we also need a 3 up here. Okay, so then the red 3 we have there is really just a constant times that function up top. So think about that red 3 is just sitting out in front of the limit. And then what we're applying the theorem to is this part, the limit as x approaches 0, sine 3x over 3x. Times that 3. And that whole limit in blue is equal to 1. Therefore, the entire limit is equal to 3. Does anyone have any questions on that? Kind of like have to manipulate it so that it fits that limit above exactly.
Is there an example of that where we could just look at the first version of that and just say, oh, this is going to be 3 because that's the coefficient there?
Right. Yeah. So like, yeah, and technically, if we were going to show that that's 3 over 1, right? It should be 3. You have to look at taking something like we have here and proving that. So like if we don't prove that, then that's just a statement by itself. But yeah, once you see a few of these, like you start to see the pattern that emerges. And you could, some of these you could look at and be like, oh, that limit's just going to be 3, or that limit's going to be 1. So like something like the limit as x approaches 0 on the sine of 5x over 3x. So what would we suspect that is going to turn out to be? 5/3. Okay, so I mean, maybe that's our hunch. We have to show it though. We can't just say it's 5/3, right? How do we know it's 5/3? That's just our hypothesis. It's 5/3. So let's see if it's actually 5/3. Again, we want the argument of sine to match the argument of the denominator. So this is just a 3 times the thing on the bottom, right? We can look at that as 1/3 times the limit. Like that. And then what do we need to do?
Multiply it by 5.
We need a 5 on the bottom so it matches the argument of sine. But again, just multiplying the bottom, not allowed. We're going to multiply the top and the bottom by 5. And again, just like in that last example, that red 5 on top is going to come out front with that 1/3. So we're going to put that out front. And then we have our result that we guessed. So that's 5/3 times 1, which is 5/3. So yeah, I mean, on the homework, you don't have to show work, so you can just type in 5/3. But I would recommend working through these.
So, aside from number 3, are you essentially just multiplying that fraction by 1, but just using whatever number for 1 that's in numerator and denominator?
Yeah, right. Yeah, we're just multiplying these by a form of 1. And then so sometimes it's not as straightforward when we start mixing these things together. So like in example 4, we'll look at the limit as x approaches 0 of sine of 5x over tangent x. And now we don't have a reasonable guess. We might guess that it's 5 based on what we've seen, but then that tangent kind of messes stuff up. So, you know, the context of what we're working with gives us a bit of a clue on what we need to happen. So we need this limit here as x approaches 0, specifically on the top with the sine of 5x. We could start off by saying, well, if we had that divided by 5x, that would be awesome, because then we could just apply the formula to that. But we still have this tangent down here as well. So if I'm going to divide the numerator by 5x, then I have to divide the denominator by 5x. So that's easy in the sense that we can apply the limit theorem directly to the numerator, but is it going to work out that we can compute that limit on the bottom, tangent x over 5x? So we'll put an asterisk next to this. We know we can compute the numerator, but we need to see if we can sort of whittle the tangent x over 5x down into something that we can actually work with. So we're gonna just take that off to the side, and what can we do with that? So again, think about what we're given and how might that guide our choice on what we want to do with tangent. So we're given two limits in terms of either sine or cosine, right?
Well, we have to get the sine part, like the sine x over x, over the cosine x minus 1. over x for tangent? Is that possible?
Kind of, yeah. I mean, you're thinking in the right direction, but tangent is just what? Sine over cosine. So let's see if we rewrite tangent like that, is that going to help us? And so that simply becomes the sine of 5x over, sorry, the sine of x over cosine x 5x. So we'll just put that 5x in the denominator. Here. Okay. And then again, thinking in terms of that limit, is that going to be conducive to write it like that as x approaches 0? What about if we just looked at this right here? Can the limit apply to that? So let's look at it like this. That's the sine of x over x times what?
1 over 5 cosine x.
1 over 5 cosine x. So the limit will take care of what's in red. Can we compute the limit as x goes to 0 on 5 cosine x without that being 0? What does cosine approach as x approaches 0? 1.
Yeah.
So there's no problem here. Cosine doesn't approach 0. We don't have 1 over a 0 situation. The theorem applies to sine x over x. So I mean, we had to break it down a lot to see, but the theorem does handle this, at least a part of it. The other part, 1 over 5 cosine x, there's no issue with computing the limit as x approaches 0. So that's what we're going to write this as. Remember, the limit of a quotient is the quotient of the limit. So we can take the limit of the top divided by the limit of the bottom. Theorem applies directly here. We did simplify the tangent x over 5x. We simplified it to sine of x over x times 1 over 5 cosine x. So according to that theorem, the limit of the numerator is 1. The limit of sine x over x in red, again, is 1. And what's the limit of x approaches 0 on 1 over 5 cosine? 1 over 5. So we have 1 divided by a fifth, which is 5. So I mean, at least based off of that example, we might guess if I have the sine of ax over the tangent of bx, that the limit would be a over b. But we would need to justify that somehow. You could justify it exactly how we justified this, with with a's and b's instead of 5s and 1s. Okay, does anyone have any questions on any of those? All right, so then we're going to use those limits to figure out what is the derivative of cosine. So like the next page will have the formula for all of our trig derivatives, but this is kind of what we have to start off with. We have to say that the derivative of this function, f prime, is the limit as h approaches 0 on f of x plus h minus f of x all over h. So we're just using this to show where the derivatives come from. You don't, whenever you're asked to find the derivative of trig functions on the exam, please don't compute the limit as h goes to 0 on them. we're just deriving these limits, showing where they come from. Your textbook, I believe, goes through the sign, the derivative of sine in the same way. But the trick for either one of those is we're going to utilize those limits and the sum and difference identities for sine and cosine. So cosine, we'll just write it here, of x plus h or of a plus b is the cosine of x times the cosine of h minus the sine of x times sine of h. So that identity, probably long forgotten, but utilized here, and that's how we're rewriting cosine of x plus h. Okay, so what that allows us to do is just have things in terms of sines and cosines, not sines and cosines of something plus something else. And then we can factor out, from these two terms here, we can factor out a cosine x. So basically, like one more step before we do that, we're going to break this up. We're going to look at it as the limit as h approaches 0 on this thing. Minus cosine x all over h times the negative sine x sine h over h as well. Because these things are all separated with addition and subtraction. In theory, all three of those things up top are really divided by that h. So we're just going to split them up so that we have our cosines over h and our sines over h. Is everyone okay with that step? Yeah.
Might be a dumb question, but I'm just trying to refresh my memory. Where did the minus sine x sine h come from?
Just from this identity, the cosine of something plus something, that's just the identity for cosine of a plus b. So that's where the minus sine x sine h came from. All right, and like we said, we're going to factor from this first term, or this first factor rather, we're going to factor out the cosine x. Cosine h minus 1. All over h. Remember when we compute the limit of a product like this, the limit does distribute over the product. It's just that the derivative does not, but a limit does. So this is also multiplied by the limit as h goes to 0 minus sine x sine h all over h. So it looks, at this point, it looks kind of messy because we've got x's and h's, but we are computing the limit as h approaches 0. The limit operates on things that involve h. The limit does not operate on things involving x. So the things involving x we can take outside of the limit. So like this cosine of x can come out front and multiply that limit. Same thing with this sine x here. Okay. Do we know what this limit equals?
Did we lose this negative sign somewhere?
Oh yeah, negative sign here. take that out. Yeah, the limit there is 1 by our theorem. What about this limit here? Zero. So that's all 0. Oh, we lost a plus though somewhere. I don't know why we have this this multiplication
Oh, right
here.
there, yeah.
Yeah, right here. No one caught that? That's not multiplied. I don't know why that's there. All these things are separated by addition and subtraction. So it's still, if we're going to put the minus sign there, we'll just have this as plus. We move the minus sign out front, it'll just be minus that thing. Okay, sorry about that. So this whole thing on the left is 0 minus our sine x times this 1 right here. So all we get is minus sine x. So that is the derivative of cosine. The derivative of cosine is negative sine. We're just going to use that now. You don't have to go through the limit procedure. Just like we know the derivative of x squared is 2x, shortcut derivative cosine is negative sine. We do the same thing for sine, and then when we find the derivative of tangent, we write it as sine over cosine, and then just utilize the quotient rule for the other 4 trig functions. Okay, so there's the derivative of our trig functions. You kind of get like all 6 of them if you can remember the 3 on the left. And I guess the mnemonic that sort of works here is replace function with its cofunction. And negate the derivative. So like for instance, if we remember that the derivative of tangent is secant squared, then the derivative of its cofunction, cotangent, is negative cosecant squared. So we cofunction these things and turn the result into a negative. Derivative of secant tangent, derivative of cosecant is negative cosecant cotangent. The only exception there is sine and cosine. Like the cosine is really sine. That's the kind of weird one. But we know the derivative of sine is cosine, the derivative of cosine is negative sine. So I mean, I guess in effect, you know 3 of them, you get the other 3 if you can remember that. Otherwise, you just remember all 6. All right, so again, I would have 6 different flashcards with these derivatives on them. Look at them every day. So like for tangent, what we were saying is like we can get all of these since they're just reciprocals of sines and cosines. The derivative of tangent can be thought of as the derivative of sine over cosine. So we really only need to prove the derivative of sine and cosine. We've already kind of used the quotient rule. And we'll see that's quite common with some other derivatives as we learn other derivative rules. Instead of like computing the derivative using like that limit definition, we'll use another derivative technique to find the derivative instead. We have the bottom times the derivative of the top minus the top times the derivative of the bottom. And we have all of that over the bottom squared. Okay, so we have cosine times the derivative of sine. Derivative of sine is cosine. Minus sine times the derivative of cosine, which is minus sine, all over cosine squared. So what happens to the top? What's cosine squared plus sine squared? 1. 1. Yeah. Remember cosine was like the x-coordinate, circle radius 1. Sine was like the y-coordinate. Unit circle, that's where sine and cosine came from. Yeah. So that's like a fundamental identity with sine and cosine. So the top is just 1 over cosine squared is secant squared. Derivative of tangent is secant squared. So in honesty, if you forget, if you just remember sine and cosine, you still have to remember the product rule, and the chain rule, and some things about trig functions. But the other 4 you could get using the quotient rule, and when we get there, the chain rule in 3-7, either or. But definitely need to know those. And so the thing is the textbook doesn't really go slowly with this stuff. It's like, hey, here's the derivative of the trig functions. Now we're going to apply the trig functions as products. We're going to divide trig functions with other functions. And so now this is where the chain rule, or the product rule and the chain rule, are also still in effect. Okay, so find the derivative of e to the x times cosine x. Of course, you need to know the derivative for both of those because we're dealing with a product. We have to use the product rule. So product rule. So the first times the derivative of the second plus the second times the derivative of the first. And I know it seems like, it's at this point maybe trivial to write out explicitly d over dx of e to the x because you already know that's e to the x. Again, I just strongly recommend writing out these derivatives before you actually take a derivative. So we have e to the x times cosine, the derivative of cosine. Derivative of cosine is negative sine. So wherever you want to put that, maybe just here, negative sine x e to the x plus e to the x cosine x. And there's the derivative of that. Any questions? Still a product rule, just a new function we have to remember the derivative of. Okay. Another example, compute the derivative of tangent x over 1 plus tangent. So the structure of that function is a quotient, so we need to apply the quotient rule to that. We take the derivative, it's the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, don't forget that bottom squared part. I see a lot of people on the exam just taking the derivative, top derivative of the bottom minus whatever. Like, it has to be over the bottom squared, otherwise it's not the quotient rule. So don't forget that. What's the derivative of tangent?
Secant squared.
Secant squared. What's the derivative of 1 plus tangent?
Secant squared.
Also secant squared. So we have 1 plus tangent times secant squared. Minus tangent times secant squared again. And that's still over 1 plus tangent squared. You have some like terms on top, so I don't think it's too much of a stretch to simplify this. You've got a secant squared plus a secant squared tangent minus a secant squared tangent. So those things are going to cancel out. We're left with just a secant squared on top over that square on the bottom. Secant squared over 1 plus tangent squared. Remember, that's not the same. If you maybe vaguely remember the identity, the identity is 1 plus tangent squared is secant squared. But this isn't the same thing as this. So that's 1 plus tangent squared plus 2 tangent for this one. So we're going to just leave it like that. Does anyone have any questions? Okay. Second derivatives of these things we can find as well. So like if you haven't started the homework, you probably should. There's only 2 sections in chapter 3 that don't have new derivative rules. All of the other sections do have new derivative rules. And every time we learn a new derivative rule, everything that came before that is all fair game with the new derivative rule. So it compounds very quickly. Okay, we already saw the first derivative of tangent is secant squared. Remember, that's just secant x quantity squared. So to find the second derivative, we need to take the derivative of the first derivative. So how are we going to do that?
Power rule.
The power rule?
Family.
So remember, the power rule applies to what to a power? It's just
Oh, X.
so it's just the variable, right?
Yeah.
That's not what we have here. It's not as simple as saying it's 2 secant to the first. What we're actually looking at here is the derivative stuff we see in 3.7, because what we're thinking of this is some function of x. We know it's secant, but it's a function of x being squared. So what you have there is actually a composition. You have one function put inside another function, right? So like if f of x were secant and g of x were x squared, then we put those together. We put secant inside of that, so we have g composed with f of x. So that's what we're looking at. Unfortunately, like we said, the power rule just doesn't apply. This is in 3.7 chain rule. So we can't apply the power rule to that.
Would we have to put secant squared times secant squared when you use the product rule?
Right. So we have a product rule here. It's secant times secant. So now we're going to use the product rule to do that. After 3.7, we will be able to find the derivative of secant quantity squared. But we have to talk about the chain rule first. We have it. So product rule. And so, like, you can see, like, there's a need for that rule, right? Like, if I said, hey, here's a function, you know, take the derivative of this. This is no longer equivalent to taking the derivative of just x to the 100th power, which is 100x to the 99th. There's an additional step that we need to take that. So it's impractical to multiply this thing by itself 100 times, then, you know, or have 100 products here and use the product rule. So there is a necessity for another kind of rule because we've only talked about trig functions, quotients, and products. We know there's like, millions of other types of functions that doesn't cover. So we have the first times the derivative of the second plus the second times the derivative of the first. And the derivative of secant, it would be what?
Secant tangent.
Secant times tangent, right? So that's secant tangent. Same thing with this one. Secant tangent. Those are multiplied by our secants here. This secant, and this secant. And our plus. So we have two of those. We have two secant squared tangent. And that's our y double prime. When our y was y prime rather. So you can see, like, the power rule is involved, right? We still have that coming out, the 2 multiplying the secant squared, but it's a little more involved than that. So let's write it like this, just so we can maybe start thinking about what has to happen. So it's secant x times secant tangent.
Which is the derivative of secant.
Which is the derivative of secant, right? So we can sort of see the power rule here. When we said what's the derivative of secant squared, it wasn't quite the power rule because that would have just given us 2 secant to the first. We have an additional factor of secant tangent, which we know is the derivative of the secant. So it's like if we're applying the power rule, we also have to apply an additional derivative. Like this thing right here, we could say the derivative of a function squared is 2 times the function, but it has to be multiplied by the derivative of the function as well. And that's essentially the chain rule, which we'll talk about in 3.7. But I think, we have the capability to sort of allude to it right now, so that's what we did. Anyone have any questions? Our second derivative, 2 secant squared tangent. Okay. All right, well, if there aren't any questions, we're gonna head on to chapter or section 3.7. We're supposed to start 3/7 today. So 3/6 is at the end. 3/6 is in an application section, as well as 3/11. So I've just put those at the end of chapter 3. So we're just doing the application stuff at the very end, getting all of the derivative rules out of the way. All right, the chain rule, and you've sort of been doing the chain rule all along. So like, if we just go back for a second and look at the derivative of x cubed, when we say that's 3x squared, kind of what we're not seeing or what we're not writing is also this thing is multiplied by 1, right? So we just don't write that. But this 1 that we're multiplying by actually comes from the derivative of just this x. So we're saying it's 3x squared by the power rule, 3x squared, but then we're also multiplying by the derivative of the thing on the inside, which is just x, which is just 1. So you've kind of been doing the chain rule all along. It's just we haven't explicitly said that you're doing that. So anyways, the idea is there's 2 versions presented in this theorem. Version 1 says that, well, we'll talk about this in a minute. We should say the chain rule is allowing us to take the derivative of compositions. Start putting functions inside of other functions. Okay, so it says suppose that y, which is f of u, is differentiable at u, which is g of x. So there's u, which is g of x, right? U and g of x are the same, which means we could read this as f of g of x. They've just already made that substitution. Let u be g of x, but this is the same thing. Suppose y is equal to f of g of x. G of x is differentiable at x, its input. The composition then, f of g of x, is differentiable at x, the input here for g, and its derivative can be expressed in 2 ways. So the derivative of y, this thing here, here's y, the derivative of that function with respect to x is the derivative of y with respect to u. And remember where this comes from, this dy over du is this thing right here. We're taking the derivative of y, which is a function of u. So we would have like y equals to u squared. We have to take the derivative of that with respect to u. So that's dy over du multiplied by du over dx. So u, right here in green, u is g of x. U is a function of x, the derivative of that function with respect to x. So that's from this one. This is from our substituted version of that function. So we'll go through a couple using both versions, just to see whichever one you prefer. But the idea is that in order to use this first version, version number 1, is you have to perform a substitution. And the substitution is, it's saying let u equal the function on the inside. Oops. Let u be the inner function of that composition, if you will. I'm going to erase some of this stuff. So we'll just state that this method involves a substitution where u is equal to the inner function. second version just says that in order to take the derivative of a composition, we take the derivative of f. So notice in this first factor here, the derivative of f with g and still on the inside. So all we've done is taken the derivative of the outer function, left the inside function alone, and then we've multiplied all of that by the derivative of the inside. So I don't know, I guess we could try to write that out in words. The derivative of a composition is the derivative of the outside or the outer function and then importantly here, when we say the derivative of the outer function, you have to leave the inner function alone. So it's the derivative of the outer function still evaluated at the original function on the inside. Evaluated at the inner function. In other words, that one's left alone times the derivative of the inner function. So if you don't remember like compositions, you probably need to take a quick glance at them because it's like how do you take the derivative of the square root of sine x, or how do we take the derivative of the e to the tangent of x squared? Like all of those functions are showing up in 3.7. So this rule definitely adds a lot of complexity to our derivatives. So y'all have any questions before we go? See y'all.